Alright, welcome to our last practice exam video. So this is just covering the Chapter 8 content. So of course for the final is cumulative. You have to, I would recommend going back to the previous practice exams and making sure that you're good with all that stuff as well. But anyway, we're just focusing on Chapter 8 stuff today. Does the following IVP have a unique solution? So dx dt is equal to this matrix times x plus this column, and x of 0 is equal to negative 4, 2. So all of the entries have to be continuous on some common interval which contains this point t equals 0 in this case. But 3 ln of t is not continuous at 0. It's not even defined at t equals 0, and so because of that, the answer is going to be no. So 3 ln of t is not continuous or even defined at t equals 0, so the answer would be no here. Okay. This is my second take doing the video, so I can just undo and redo here. Anyway, moving on. Determine whether this IVP below has a unique solution. So this is like the same problem, except for this turned into x of 5 instead of x of 0. And so now we just have to say, like, all right, well, is there a common interval for all these other functions? So 7 over t squared minus 1 is continuous everywhere except for 1 and negative 1. 3 ln of t is continuous for any positive value of t. 3 e to the t, negative 1, t to the fourth, and so those three are all just always continuous, and then 5 over t minus 1 is continuous except for t equals 1. So these are all continuous. Now we need to find a common interval that they're all continuous on, which contains the point t equals 5. And so the interval we should pick would be 1 to infinity, just to avoid the problem points of 1, negative 1, and 0. And t equals 5 is contained in that. Like, we could have also had the options of negative infinity to like negative 1, or negative 1 to positive 1. And then we had like our option of 1 to infinity. Just throwing out, oh sorry, I forgot about 0. Negative 1 to 0, 0 to 1, and then 1 to infinity. These are like our 4 options because we had to throw out negative 1, we had to throw out 0, and we had to throw out positive 1. And then we just look for which of the 4 intervals is t equals 5 contained in. So if this was like x of a half, we would have had to go with like 0 to 1. But it's x of 5, so this is correct. Show that this is a fundamental set for the following differential equation. So this amounts to showing 2 things. You have to show that these are both a solution to dx dt equals a times x. We have to do it for both of them. And then we also have to show that they are linearly independent. So let's show that they satisfy the dE first. And we'll do it one at a time. So for x equals e to the 2t, e to the 2t, this one's more straightforward. Dx dt is equal to 2 e to the 2t, just taking the derivative, just using the chain rule. Both of those, and then a times x, 3 negative 1, 1, 1, times e to the 2t, e to the 2t. This equals 3 e to the 2t minus e to the 2t, and then 1 e to the 2t plus 1 e to the 2t, which simplifies to 2 e to the 2t, 2 e to the 2t, which is exactly what we got when we computed dx dt. So that's the solution. What about t plus 1 e to the 2t and t e to the 2t? Well, dx dt, we're going to have to do some product rules in here Derivative of t plus 1 is just 1. And 1 times e to the 2t plus t plus 1 times the derivative of e to the 2t, which is 2 e to the 2t. Write it like that. And then derivative of t e to the 2t is e to the 2t plus 2t e to the 2t. Again, just doing some product rules. And then a times x is equal to 3 negative 1, 1, 1 times what we had. Simplifies down to 3t plus 1 e to the 2t minus t e to the 2t, and then t plus 1 e to the 2t plus t e to the 2t. How does this simplify? Because, we're trying to show that this and this are equal, and then this and this are equal. So this can be written as 3t plus 3t e to the 2t plus 3 e to the 2t minus t e to the 2t, and 2 t e to the 2t plus e to the 2t plus t e to the 2t. What's that? That is this and this combined to make 2t e to the 2t plus 3 e to the 2t, and then this and this combined to make 2t e to the 2t plus e to the 2t. And this still doesn't look exactly like this, so let's maybe go a little further up here. This is e to the 2t. No, I'm going to make some more space here, actually. So just distributing out the e to the 2t to the 2t plus 1. And this becomes 3 e to the 2t plus 2t e to the 2t, and then e to the 2t plus 2t e to the 2t. And wouldn't you know it, those are equal. And then step 2 is to show that they are linearly independent. We do that by computing the Wronskian of, I'll call them x1 and x2. So e to the 2t, e to the 2t, t plus 1, e to the 2t, and t e to the 2t. Now we just take a determinant of all this stuff after making space. So this is t times e to the 2t times e to the 2t. That becomes e to the 4t minus t plus 1 e to the 4t. That simplifies down to t minus t plus 1 e to the 4t, which is just equal to e to the 4t, which e to the 4t is just never equal to 0, so this Wronskian is non-zero, so they are linearly independent. All right, let's get into solving some d's. dx dt is 3, negative 13, 5, 1, and times x. And x of 0 is equal to 3, negative 10. So first step is compute the characteristic equation. I do the determinant, vertical bars, 3 minus lambda, 5, negative 13, 1 minus lambda. So this is the determinant of a minus lambda I. Remember that the identity matrix is just 0, 1, 0, 0, 1. And then so lambda times that would just make those lambdas along the diagonal, so we get this. All right, 3 minus lambda times 1 minus lambda, and then minus. Remember, determinant is this times this, minus this times this. So minus 5 times negative 13, that's plus 65. We have the double negative introduced there. This is lambda squared minus 4 lambda plus 3. All right. Let's see. How does 68 factor? That's like 34 times 2, 17 times 4. Don't like that. All right, well, maybe we have to do the quadratic formula for this. I wrote this like a week ago. I already forgot how it works out. All right, if I do the quadratic formula, I get lambda is equal to negative b plus or minus square root of b squared minus 4ac over 2a. All right, so if this discriminant works out nicely, then I think we'll be in good shape. Okay, what's 4 times 68? 272. Yeah, that's negative 272. And then negative 272 plus 16 is negative 256. Yeah, okay, cool. So we have to, yeah, this is good. All right, this is plus, so 256 is 16 squared. So square root of negative 256 is 16i. So this is 2 plus or minus 8i. And so, yeah, these would be our eigenvalues. We need our eigenvectors next. So let's just stick with lambda 1 equals 2 plus 8i. And we only need to figure out one eigenvector here. So a minus lambda 1i is equal to 3 minus 2 plus 8i, negative 13, 5, and then 1 minus 2 plus 8i. So this is 1 minus 8i, negative 13, 5, and then negative 1 minus 8i. Okay, and now we want to row reduce this thing. So technically this is like inside of an augmented matrix with zeros on the right-hand side because we're really solving a minus lambda I times x is equal to 0 and solving blah, blah, blah. We're just going to do row operations, whatever. All right. So you want to multiply one, multiply a... how do I say? Yeah, scale this row so that this is going to match up with 5. What do you multiply 1 minus 8i to give you 5? I have no idea. Whenever you're trying to get rid of imaginary numbers here, or even like square roots, like it always comes down to the or it often comes down to the trick of multiplying by the conjugate. The conjugate of like a plus bi is just a minus bi. So just multiply that row by not 1 minus 8i, but 1 plus 8i. So let's take row 1 and multiply it by 1 plus 8i. Let's see what happens. So 1 minus 8i times 1 plus 8i is going to be 1 squared minus 64i squared. And then negative 13, 1 plus 8i, and then 5, negative, I'm going to just factor out a negative here. Okay, what is this? Well, I squared is equal to negative 1. So, and that's because, remember that I is equal to the square root of negative 1, so I squared is equal to negative 1. So this becomes 1 plus 64, or 65. And now it's pretty obvious that this row is just 13 times this row. So I'll just add negative 13, row 2, add that to row 1, just to zero that out. Now I get 5x minus 1 plus 8i y is equal to 0, and so my eigenvector will be, let's pick, so if I just pick x to be 1 plus 8i and pick y to be 5, then this equation is going to be satisfied just plugging these values in. So you can usually just like kind of replace these, like swap these coefficients with each other, and you know, accounting for the negative sign correctly. So here these are both going to be positive, and this is going to be our eigenvector. So now we can get our general solution. So we're going to have an x1 and an x2. And I don't remember what they're going to be, but they are up here, so I'm going to copy paste that. Okay, so x1 is e to the at. What is a? This is a, this is b. A is 2, b is 8. Oh, what's u, what's w? Split v into the real part plus the imaginary part. So this is like 1, 5 plus I times 8, 0, because this doesn't really have an imaginary part. And then this would be our u, and this would be our w. So this is 1, 5 cosine of 8t minus 8, 0 sine of 8t. Gosh, why? Okay, whatever. And then e to the 2t 8, 0 cosine of 8t minus 1, 5 sine of 8t. That should be plus. I'm just gonna add a page here. So why not? All right, so general solution, c1 x1 plus c2 x2. And we need to satisfy x of 0 is 3, negative 10. So plugging all that stuff in, we get c1 times x1 of 0. x1 plugging in 0 is e to the 0 times 1, 5 cosine of 0 minus 8, 0 sine of 0 plus c2 times x2 of 0, which is going to give me e to the 0 times 8, 0 cosine of 0 plus 1, 5 sine of 0. Cosine of 0 is 1, sine of 0 is 0. So this becomes c1 times 1, 5 plus c2 times 8, 0, because this will go away. And this has to equal 3, negative 10. All right, so throwing this into an augmented matrix, get this. I'll do negative 5 times row 1, add it to row 2. Wait, do I want to do that? No. I'm just going to divide row 2 by a fifth. That'll be more efficient. So that gives me 1, 0, negative 2. Now I'll do negative row 2 added to row 1. Okay. Cool. All right, so this is telling me 8c2 is equal to negative 5, and then the second row is telling me that c1 is equal to negative 2. So c2 is equal to negative 5 over 8. So our solution is x equals c1 e to the 2t 1, 5 cosine of 8t minus 8, 0 sine of 8t minus 5 over 8, because that's our c2, e to the 2t. I'm pretty much just copying from this line. Just remembering when I plugged in 0, I'm just going back in terms of t. And then just using the correct C1 and C2 choices. Yeah, really just using all that stuff there. All right, and that would be our general solution. Or not general solution, that is just our solution to the IVP. All right, cool. Almost done. All right, dx dt is equal to x plus 2y, dy dt is equal to 3x plus 2y, x of 0 equals 0, y of 0 equals negative 4. First step is to translate this into a matrix equation. So 1, 2, 3, 2 is our coefficient matrix. This times x is equal to, I'll just write x prime, y prime, but really this is saying x prime is equal to a times x, or dx dt is equal to a times x, where this is our dx dt, and a times x, this is our a. So characteristic equation, a minus lambda I, and determinant is equal to 1 minus lambda, 2, 3, 2 minus lambda. Multiply diagonals, and then minus this times this, so minus 6. We get lambda squared minus 3 lambda plus 2, and then plus 2 minus 6 is minus 4. Let's double check that. Lambda squared minus 2 minus 1 minus 3 lambda plus 2 minus 6 minus 1. Okay, cool. This factors as lambda minus 4 times lambda plus 1. So our eigenvalues are 4 and negative 1. Great, this problem's gonna be not so bad because these are distinct eigenvalues. Whenever you have the distinct eigenvalues, it's generally easier to go about solving the problem, I think. All right. So eigenvalues for lambda equals 4, or eigenvalues for lambda equals 4. So a minus 4I is equal to 1 minus 4 is negative 3, and 2, 3, and then 2 minus 4 is negative 2. I can just add row 1 to row 2. So negative 3x plus 2y is equal to 0. So you can make x be 2, and if you made x2 and y 3, then that would satisfy the equation. So your eigenvector would be 2, 3. What about for lambda equals negative 1? A plus I is equal to... okay, so 1 plus 1 is 2, and then 2, 3, and then 2 plus 1 is 3. I could scale down row 1 by a half, and then add 3 times row 1, add it to row 2. So this is telling me that x plus y is 0, so I can make x be 1 and then y be negative 1. My eigenvector would just be 1, negative 1. Awesome. So our general solution is x equals c1 e to the 4t times that eigenvector plus c2 e to the negative 1t times that corresponding eigenvector. And we need x of 0. Oh, that was technically up here as well. X of 0 is equal to 0, negative 4. Yeah. Okay. So this tells us that c1 e to the 0, 2, 3, plus c2 e to the 0, 1, negative 1, has to equal 0, negative 4. These are both just 1, so I could put this into an augmented matrix and solve it. This one won't work out quite as nicely as the other one, but that's fine. What could we do? Let's maybe just scale row 1 down by a half. We'll do negative 3 times row 1, add it to row 2. Negative 3 halves minus 1 is negative 5 halves. And then that just stays at negative 4. I want this to be a 1, so let's multiply by the reciprocal. Negative 2/5 times row 2. And so that becomes 8/5. Negative a half times row 2, add it to row 1. Becomes negative 4 4 over 5. So kind of gross numbers, but it is what it is. This tells us that C1 is negative 4/5 and C2 is positive 8/5. So our solution is x equals C1 e to the 4t times 2, 3 plus C2, which is 8/5 e to the negative t 1, negative 1. I like to check my answer at this point just to be confident that what I have is right. So if I plug in t equals 0, do I actually get 0, negative 4? So if I plug in t equals 0, this is just 1. And then I get negative 4/5 times 2 plus 8/5 times 1. What to do? Negative 4/5 times 2, I get negative 8/5, and then plus 8/5 times 1, that is actually equal to 0, so that's good. And then negative 4/5 times 3 is negative 12/5, and then 8/5 times negative 1, negative 8/5, so this becomes 0, negative 20 over 5. Negative 20 over 5 is negative 4, so that's a good check. Just a reality check just to make sure that this is satisfying the things we needed to satisfy. Okay, technically this is our final answer should be in terms of x and y. We should be saying like, oh, x is equal to negative 4/5 e to the 4t times 2x, because this is like our x value. And then plus 8/5, like e to the negative 2. I'm not going to care too much about that if you get your answer and just keep it in matrix form. I am more than happy with this, but you will see like some places like online or whatever might tell you that if it's phrased like this, that you should convert your final answer to be x's. Oh, sorry, that was... I put like x's when it should have been t's. Okay. Let me just explain what I'm trying to say real quick. So if I were to combine all this stuff, this would be negative 8/5 e to the 2t plus 8/5 e to the negative t. And this would be negative 12/5 e to the 4t. Sorry, that should be 4t as well. Minus 8/5 e to the negative t. So you could write this in terms of x and y. Just say x is equal to negative 8/5 e to the 4t plus 8/5 e to the negative t. And then y is equal to negative 12/5 e to the 4t minus 8/5 e to the negative t. So this would probably be like the best final answer for this, but I'm just gonna say it is fine with me if you just keep this in matrix/vector form. Just kind of shrink that, throw that over there. All right, cool. Last problem. Find the general solution to dx dt equals All right. Eigenvalues: 0 minus lambda, negative 1, 9, negative 6 minus lambda. Take a determinant. I multiply diagonals, that diagonal minus that diagonal. That becomes negative lambda times negative 6 minus lambda minus negative 9. Double negative makes positive. I can distribute this negative to make all that stuff positive. So this is lambda squared plus 6 lambda plus 9, which factors as lambda plus 3 squared. So negative 3 is our only eigenvalue. So if I do a minus lambda I, so that double negative becomes plus 3i. So adding 3 to all the diagonal entries over here gives me this. I can do -3 times row 1, add it to row 2. Get this, which tells me that 3x minus y equals 0. So I can pick x equal to 1 and then y equal to 3. So 3 times 1 minus 1 times 3 is equal to 0. So our eigenvector v is equal to 1, 3. Okay. So what do we do from here? So if you're not sure, you're stuck, there's some helpful symbols up here. So this is where you're going to want to use this information. So your second solution is going to be given by x equals e to the lambda t times tv plus u, where this u is an unknown. What is the u? Well, it has to satisfy this equation right here. A minus lambda I times u is equal to v. So we need to find u by solving that equation. So we need a minus lambda I times u equal to that vector v, which is 1, 3. So 3, -1, 9, -3 times u is equal to 1, 3, which we could throw that into an augmented matrix and then just row reduce. We're just going to do -3 row 1, add it to row 2. Can usually, I think always probably do just the same row operations that you do up here, down here, and then it's just going to work out because not positive that works for like higher dimensional cases, but it definitely seems to always work down here. So if I do -3 times this row, add it to this row, I get -9, +3, -3, cancels all the stuff down there. This tells me 3x minus y is equal to 1. Now I just have to pick some x and y values. So let's see, probably easiest to just pick x equals 1 here because this is like being multiplied by a 3 and I want to have some whole numbers in my vector. If I do that, then I get 3 times 1 minus y is equal to 1. Solving for y, you get y is equal to 2 there. So our u is going to be 1, 2. Then our solution will, okay, our x1 is e to the lambda t times our eigenvector. And our x2 is going to be e to the lambda t times t times that vector plus u. So our general solution is x equals c1 e to the -3 t13 plus c2 e to the -3t t13. I don't know why 3s are just so difficult for me to write sometimes. Plus 1, 2. Apparently 2s are difficult as well. Okay. And yeah, hopefully I didn't make any mistakes doing that. But I think that should work out. Yeah, this all seems relatively fine to me. If you see any errors, obviously just throw it in the comments. It's, you know, like I'm kind of recovering from food poisoning from last night, and so I'm very out of it. And so if I have any like computational errors anywhere in this, I apologize. But please just, you know, help me out, help your classmates out. Just throw a comment down with any fixes, or if you have any questions about it too. Yeah, good luck studying for the final.